Did you know that the natural logarithm function was defined before e to the x? Historically speaking, that's not the way we teach it in classes, right? We teach e to the x first, and then we say ln of x is the inverse function of e to the x. Historically, that didn't happen that way. Historically, the natural log function was motivated by the fact that we'd like to be able to integrate, I'm going to use the variable t here instead of x, 1 over t dt, based on the fact that, well, you can't figure out what an antiderivative of this is using the reverse power rule. Remember, the reverse power rule says that the integral of, I'll use x over here, x to the n dx is x to the n plus 1 over n plus 1 plus c. There's your general antiderivative, but of course you can't use that formula when n is -1. This is if n is not equal to -1. But 1 over x, or 1 over t if you prefer, is certainly a nice continuous function when the variable is positive and also when it's negative, not 0, because you'd be dividing by 0. So this integral should make sense. Effectively, what happened, I'm not sure who did this back in the 1600s, they defined the natural log of x by this integral where we're going to do a definite integral from 1 to x. This was essentially the definition of the natural log function. In other words, if you graph 1 over t as a function of t, it looks like this. And when t is 1, the output is 1. These axes are not the same scale. And for a value of x greater than 1, say right there, ln of x is the area under the curve right there. That area equals ln of x. If x happens to be between 0 and 1, the formula, the integral is still the same, but you'd have to interpret it as the opposite, the negative of the area under the curve between x and 1, if x were over here between 0 and 1. So they're defining the natural logarithm this way. So how do you define e to the x? You define it as the inverse function of this function. The variable is in the upper limit of integration. But how do you know an inverse function exists? Based on the fundamental theorem of calculus, we can say that the derivative of this function is 1 over x. Based on this integral formula, it follows by the fundamental theorem of calculus, FTC, that the derivative of this natural log function that we're pretending like we're defining for the very first time is 1 over x, which is certainly a positive quantity when x is positive. And therefore, ln of x, this function that we're pretending we're defining for the very first time, is increasing, strictly so, for x positive. It's got a graph that's going up. Don't want to dwell on this a whole lot. Our main goal is to get to numerical integration, and we will be approximating the natural log function as an integral using numerical integration techniques today. But before we do that, let me just illustrate that you can, for example, derive properties of logarithms this way. The algebraic properties of logarithms, for example, that the ln, the natural log of a product, is the sum of the logs. How? Well, we know this is true. That's true because of this integral formula. The fundamental theorem of calculus says to differentiate an integral like this, where the variable's in the upper limit of the integral, you get the integrand function, but use the same variable x as you have over here. We also know from calculus that the chain rule would allow us to differentiate something like this, where a is a constant. By the chain rule, the derivative of this will be 1 over a times x times the derivative of a times x times a. Hey, those a's cancel, leaving you with 1 over x, which is the derivative of the plain natural log function. So what we have here is that the derivative of natural log of ax equals the derivative of natural log of x. They have the same derivative. Therefore, ln of ax and ln of x differ by constant. Therefore, ln of ax equals ln of x plus some constant. I could have also written that as ln of ax minus ln of x equals a constant. How do you figure out what the constant is? Plug in x equals 1. If you substitute x equals 1 into both sides of this equation, this is supposed to be true for all positive values of x. So in particular, it should be true when x is 1. You'll get ln of a equals ln of 1 plus c. But what's ln of 1? You know it's 0, but can you derive that from this formula? Sure. If x is 1, you're integrating from 1 to 1. There's no area. ln of 1 is 0. So this becomes 0 plus c, or just c. In other words, c is the natural log of a. And therefore, ln of ax equals ln of x plus ln of a. Or if you prefer, ln of a plus ln of x. We have derived a property of logarithms. The log of a product is the sum of the logs. Oh, that was fun. Let's do another one. We know that the log of some number to some power, say ln of x to the p, that power can be brought in front. This is p times ln of x, right? Property of logarithms that you've known since maybe 11th grade or something. Can that be derived as well? Sure. Same kind of method. Differentiate this. Use the chain rule like this. Simplify. X to the p minus 1 power cancels completely. With p minus 1 of these x's, you're left with p over x as a simplified version of this. And that is the same as the derivative with respect to x of p times natural log of x, right? P is a constant. P is a constant here. Hey, yeah, the derivative of natural log of x to the p equals the derivative of p times natural log of x. Therefore, ln of x to the p equals p ln of x plus some constant c. This time the constant is 0, though. If you substitute x equals 1, you get ln of 1 to the p equals p times ln of 1 plus c. Once again, ln of 1 is 0. This implies 0 equals 0 plus c, so c must be 0. And therefore, ln of x to the p equals p times ln of x. We've just derived another property of logarithms. Kind of a fun way, based on the integral definition of the logarithm, properties of derivatives like the chain rule. I also use the fundamental theorem of calculus right here to derive this formula. And then just a little ingenuity. This equation and this equation are supposed to be true for all positive values of x. And therefore, if you plug in a particular x like x equals 1, they're still true. And plugging in x equals 1 allows you to solve for c. You like that? Kind of fun? I think it's pretty cool. Of course, that's not the way we teach this in calculus, but it's historically the way people first thought about logarithms. And people came up with tables of logarithms based on the integral formula and numerical integration, which we're about to do. Okay. And then again, well, how is E defined? E is defined as the solution of the equation ln of x equals 1. We know the ln of x is an increasing function based on thinking about numerical integration, approximations, if you like. You can say that it's an increasing graph that does look like this. When x is 1, the output is 0. What is the input that gives you an output of 1? It is the number e. Not drawn as good as it should be, perhaps, but that's the idea. E is defined to be the solution of that equation, the unique solution. And then ultimately e to the x, or you could also say e to the x is defined to be the inverse function. The inverse function of ln of x. This graph is increasing. It passes the horizontal line test. It's a one-to-one function. It's got an inverse function. And you can graph the inverse function to look like this. Watch my hand there, like that, right? Exponential growth, reflection across the line y equals x. Okay. Historically, that's the way people thought about it. That's how people came up with E. Now, E comes up in other ways in math, like with compound interest, but that's not how it was done historically.